investigating intermittent stereoscopy, its effects on perception and visual fatigue. Our speaker is Ari Bouaniche. Ari has just graduated as a valedictorian from a Master of Science in Digital Creation and Publishing with a focus on virtual and augmented reality at the Université Paris 8.
Thank you, Mr. Chairman, for this introduction. So I'm going to talk to you about intermittent stereoscopy and its effect on perception and visual fatigue. And I'd like to start with a couple of facts, actually. Is this working? Yes, it is. All right, so virtual reality, which involves S3D content, is used in a growing number of industries for prototyping, for example. And it is well known that S3D aids perception of distances and curvature on the Z, or the depth axis, while it is very tiring to the visual system. All right, oops, little problem with the PowerPoint. So it felt paramount to us to safeguard the visual system of people working with such tools. The second fact was something that we actually discovered in the course of a previous experiment. We were displaying to observers S3D content, and we gradually decreased disparity so that we ended up with a monoscopic image. And this actually triggered no reaction whatsoever in observers, which might suggest that stereopsis is a rather weak cue. So we actually ended up thinking, well, could intermittent stereoscopy, and by this we understand displaying mono and then stereo stimuli or vice versa, could this be actually the best of both worlds? Aiding depth perception while being less tiring to the visual system. So this gave way to a number of research hypotheses. Could intermittent stereoscopy lead to a more accurate perception than mono, or at least a perception as accurate as stereos? And by accurate, we mean a perception evaluated against an ideal of correctness. Could it lead to a more precise perception than mono? And by precise, we mean that results would be more consistent and less scattered than monos. And could it lead to less fatigue and discomfort than full-on stereo? So from this, we extracted our 4 experimental conditions: 2 intermittent stereo conditions, stereo at beginning, in which we displayed an S3D stimulus immediately transitioning linearly for 3 seconds towards a mono stimulus, and stereo at end, a mono stimulus lasting for 4 seconds, transitioning linearly to a stereo stimulus. And of course, our 2 control conditions, full mono and full stereo. So let's now talk about our experiment proper. First of all, the experiment was preceded and followed by measurements. Some measurements we took pre-experiment and post-experiment. Stereo acuity was measured using Titmus test circles. Fusional reserves while converging were also assessed, as well as accommodative response with a Donders push-up test, as well as Donders push-up test and a flipper lens test, plus or minus 2 diopters. In pre-only, we were assessing binocular status, as was suggested in one of Lamboy's paper, by submitting subjects to the Wilkins rate of reading test and computing the ratio of words read correctly in 2D over 3D. They said that it was a good predictor of binocular status and therefore visual fatigue. And in post only, we were actually administering a questionnaire of 10 questions modeled after Zeri and Levy's source factors for visual asthenopia. while watching S3D content, and subjects had to rate their answers on a continuous rating scale, going from not at all to absolutely. So talking about subjects, we had a sample group of 60 individuals aged 15 to 38. We excluded stereoblind subjects with a simple stereofly test. And we also excluded people over 40 so that accommodative response was not influenced by any presbyopia. A quick word about our experimental tasks. So the experiment consisted of 4 tasks which were repeated 45 times each for a total experimental time of 45 minutes, including pre and post measurements. Those tasks were designed to, constrain subjects to taking depth decisions. The first task we called a positioning task. So a ball was traveling on the z-axis and passing under an arch, and subjects had to press a button when the ball was right under the arch. The second task we call the depth perception task. There were 5 spheres and 6 cubes which acted as distractors. Facing the camera, the cubes were interspersed with the spheres. They all had a random depth which was capped from -1 to +1 meter. And the subjects had to point to and select the sphere closest to them. The third task we deemed the curvature perception task. We displayed a cylinder and subjects had to decide whether it was curvier or flatter than usual. This put them in a forced choice paradigm, and I'll say a few words about this in a minute. The fourth task, was called the collision detection task. There were 2 cubes facing each other and moving in opposite directions. They disappeared from the screen right before they overlapped, and subjects had to decide if the cubes hadn't disappeared, whether they would have collided or not. Very briefly, our apparatus for our stereoscopy hardware, we had a vertical 4x3 meter screen, a retro-projected passive stereoscopy setup with Infotech goggles and DSPs. Our tracking was done by 2 ART infrared cameras, and constellations of passive markers were affixed onto the goggles and the flight stick, enabling us to track the head and one hand of the subjects, and the interaction went through the flight stick button. On the software side, this was coded in C# inside of Unity 3D, and this was interfaced with our immersive setup through Middle VR. All right, so we're now going to talk about the results for perception. We processed our results through a one-way ANOVA followed by Tukey's honest significant different post hoc test. And as for precision, we analyzed the similarity of variances with Brown-Forsyth or Bartlett tests. So these are the results for task 1, and you can see as for accuracy, then stereo and stereo at beginning are more accurate. As for precision, any condition involving S3D is more precise than mono, which has the largest scattering. For task 2, again, stereo and stereo at beginning were more accurate. And again, any condition involving S3D was more precise than mono. For task 3, this is when we come back to our forced choice paradigm, we actually fitted a cumulative normal distribution curve to our data, which allowed us to compute the point of subjective equality as well as the just noticeable difference, which you see here plotted as the standard deviation of said point of subjective equality. In that task, mono and stereo at beginning were more accurate. However, stereo and stereo at end, to a lesser extent, were more precise. For task 4, deciding whether the cubes had collided or not, stereo and stereo at end were more accurate, while no particular condition was more precise. We also had a look at response times, and what we did was we plotted the proportion of response times per half-second interval, and then processed the means of those response time through a one-way ANOVA followed by Tukey's HSD post hoc test as well. So this is for task 2, and you can clearly see that there is a similarity in the graphs between mono and stereo at end and stereo at beginning. And if we have a look at the means, well, there were definitely faster responses in stereo and stereo at beginning. For task 3, again, the similarity is clear between mono and stereo at end and stereo at beginning. And if we have a look at the means, there were faster responses in stereo and to a lesser extent in any of the intermittent stereo conditions. Now for task 4, the graphs are a little different. They're all very similar, but we thought that was because time was more constrained, quote unquote, in that task, as subjects felt compelled to actually respond right after the cubes had disappeared from screen. However, it's still interesting to look at the means of the response times, and again, faster responses in stereo and stereo at beginning. Right, if we now talk about results for fatigue and discomfort, we process the measurements for each optometric variables that we measured through single-tailed pair t-tests, as well as a one-way ANOVA analyzing the difference between post and pre-measurements. We had very few significant results, I'm afraid. There was better stereo acuity after subjects had been submitted to the stereo condition, and we wondered whether this was a sign of adaptation or a false positive. And fusion breakpoint seemed to be affected by stereo and marginally by stereo at beginning. And if we had a look at the graph for that fusion breakpoint, even if the ANOVA was not significant, it seems that stereo at end, seems to affect it the least. Now, visual discomfort measurements were processed through a one-way ANOVA for each question and a one-way ANOVA that was global, taking into account the sum of all scores for each question. And we also performed a linear correlation test between the ratio for the Wilkins rate of reading test and the discomfort declared by subjects. And there was no significant difference in subjective answers between conditions, and the coefficient, the correlation coefficient between the rate of reading test ratio and the discomfort declared by subject was very little, about 0.25. So if we now try to analyze these results, it seemed to us that there was a difference between simple environment and mental operations and more complex environment and mental operations. By simple environments, we mean environments that have only static objects or objects moving, but movement is sparse, happening only on one object, and that object is traveling on one axis only. More complex environments included more objects moving on several axes, or more complex mental operations like evaluating a curvature and not only a distance. So in the case of simple environments, it seems that disparity at task onset leads to better depth decisions, which are comparable to stereo, and that was the case for tasks 1 and 2. For more complex environments or mental operations, disparity when making the depth decision leads to generally more accurate decisions, or decisions that are at least comparable to those of stereo, and that was the case for tasks 3 and 4. If we now have a look at precision, again, the same dichotomy goes on. With, for simple environments and mental operation, S3D at task onset leads to better precision, whereas for more complex environments or mental operations, further experiments would be necessary to determine whether S3D stimuli, when decision-making, increase precision. It seems that they do for task 3, but not for task 4. So we posited that for a simple environment, it seems that the brain actually constructs a depth map of the environment, which it can keep using even after disparity cues have been removed. Now, if we have a look at response times, initial S3D stimuli accelerate response. And so we posited that if there was disparity at task onset, then the brain would trust its initial judgment, which would speed up response. If we now analyze fatigue and discomfort, or at least the few significant results that we got, well, first of all, with the results that we had, it was impossible for us to claim that intermittent S3D caused less fatigue than constant S3D. However, stereo at end, we saw, seems to affect subjects' visual systems less. This could possibly be explained by the time of exposure to S3D. So here are the proportions of responses per half-second time intervals for tasks 2 and 3, and we actually overlaid on top of this graph the percent of disparity. And it seems that for stereo at beginning, 63% of responses were given while viewing S3D stimuli, whereas for stereo at end, only 49.5% of responses were given viewing S3D. So it would seem that fatigue in S3D is proportional to exposure to S3D stimuli. All right, so let's now talk about future work. A lot remains to be done. First of all, it would be extremely interesting to assess visual fatigue more accurately with more reliable tests and measurements. So replacing the titmus test, which is known to be easily cheated because of the presence of monocular cues, by a random dot stereogram test, and replacing the subject-dependent measurements of accommodative response by measurements made with an Attal refractometer would be a good idea. It would also be extremely profitable to assess subjective visual discomfort in a better way than what we did here. Indeed, our study, for practical reasons, followed a between subjects design because it was deemed very impractical to ask people to come back to the lab 4 times in sessions spaced more than 24 hours apart to ensure full visual system recovery. But next time, it would be advisable to follow a within subject design, even if it results in more constraints for us and for the subjects. It would also be interesting to isolate stereopsis. Our results were sometimes pretty pulled together, probably because other depth cues ended up compensating for the absence of stereopsis. So suppressing those other cues as much as possible, and especially motion parallax, which was a very powerful cue, would help to isolate and study how stereopsis works. Last but not least, it would be extremely interesting to assess this depth map lifetime. If the brain indeed creates an initial depth map of its environment, then it would be extremely interesting to isolate which factors make this map obsolete and trigger its re-evaluation. All right, thank you very much for your attention. This is also a very good time for me to thank IDEFI Créatique, which is a trans-university innovative program sponsoring innovative teaching and research projects, and which funded my coming to this conference.